Hey guys, welcome back to week 22 of this series. So this week is a pretty big one. So we're officially moving on from Boyd and Vandenberghe's convex optimization to a new textbook from Hastie, Tibshirani, and Friedman, which is called The Elements of Statistical Learning, or ESL for short. So I want to pause for a second because I don't want this to feel like we're closing one book and starting cold on something unrelated. So the whole reason, I picked convex optimization first was that so much of ML theory, the loss functions we minimize, the constraints we impose, and the guarantees we get is fundamentally a optimization problem underneath. So now that we've sort of built up that machinery, convexity, duality, KKT conditions, all that good stuff, I want to go and see how it shows up inside statistical learning algorithms. And, it shows up almost immediately, like, this week, immediately. So this week, we'll cover two basic methods in ML, regression and k-nearest neighborhoods. We'll see that they are kind of opposite of each other, and that every other method in this book that we'll study is kind of like, can be interpreted as a middle ground between the two. So that's why it's important to start here. So this week I covered section 2.2, which is about terminology, and section 2.3, which is titled, Two Simple Approaches to Prediction, which splits into three parts: linear models and least squares, nearest neighbor methods, and the comparison between the two. Alrighty, so let's start with some notation here. So because the elements of statistical learning, or ESL, uses a specific setup that we'll lean on for the rest of the book. Alright, so let's denote our input variables x. So think of this as a sort of an abstract vector of variables here. So this is sort of the ground truth on what we're trying to describe or estimate or model. So if we want to isolate a single input variable, from somewhere in here, let's say position j, we call that x of j. Now, a single observation is lowercase x of I. So this is important. X is an abstract general object, and xi is one sort of realization of that. For example, say we have a bunch of houses, data on houses, and we want to predict the house prices. So one house is xi here. So here's the data matrix, what I was talking about here. By default, all vectors are column vectors. So here's something that actually confused me at first. So xi is sort of the feature vector for a single house. But in the data matrix here, that information appears in a row, not a column. So xi, so position I is this position here. In this case, I equals 2. So because each vector is a column, then we need to transpose it to fit it in the matrix. So this is sort of the second way of looking at it, the row view. So again, each entry is an observation, so maybe a house. Now there's a third way to think about the data matrix, and that's the column view. So we looked at each entry and each row, but what about the columns? So the column view says that each entry here is all the data of all the houses associated with the first feature. And this column is all the data associated with the second feature for all the houses, and so forth, up until p different features. So features could just be the data that you gathered, so like square footage or number of bedrooms, something like that. Now, of course, we have to ask the question, in machine learning, what do we actually do with this data? That actually depends on the type of output. So for quantitative problem, meaning we want to output a number, this is called a regression. And we have some model, let's call it f. F is a function, and we feed it some input x, that's our data, and we get a predicted output. It outputs y hat, which is what we think is true. So we could get a vector of outputs from the entire data matrix, or we could just pass in a single observation and get a single output here. Now for qualitative or categorical problems, this is called classification, we swap Y for G, standing for group, So if our classifier is G, then then we just estimate some group from our equation, our prediction equation. And finally, we have more than just the data here. We have data, input and output as well. So our training set is a combination of these x values as well as their associated with y values. All right, so that covers the very basic of the notation. Hopefully it makes sense and it's pretty intuitive. Here's our problem. We want to predict a house price using its features. And we're going to start with the simplest model, which is a straight line, or more precisely, a hyperplane. So say we have some points like this. The simple idea is that we want to find a line. That's not a regular line, but we want to find a line that passes through these points as best as possible. Okay, so this is the model that we're working with here. It's simply a linear combination of the inputs from 1 to p. And in this case, let's say that we have only two features. Then we have some x1 and x2, and we want to change the weights on the linear function to best fit the line. So one thing I mentioned, but I want to highlight because it directly connects back to optimization. F of x, which is equal to x transpose times beta, is linear in x. And for a linear function, the gradient is just the coefficient vector itself, right? This is because when you take the gradient of f, then you just attain your weights, your beta 1, beta 2. So think about what this actually means geometrically. The gradient always points in the direction of steepest increase of a function. So the coefficients beta aren't, just sort of abstract weights. You can interpret them directly as the direction in the feature space that increases predicted price the fastest. So if beta 1 is large and positive, moving in the squared footage direction, which is beta 1, increases your predicted price a lot. Okay, so here's a diagram to illustrate that. So here's our hyperplane in three-dimensional space, right? We have two features, and you can imagine, there's points all around this hyperplane, and this hyperplane ends up being the best fit. So we'll talk about that later, but the point is that the gradient of f is just the weight. And so the direction of steepest ascent is simply the direction that the vector of weights points. All right, so this is sort of the model and the buildup and the intuition. So now the question becomes, how do we actually find the beta vector? How do we actually find the weights that define this hyperplane here that best fits our data? So we need to define what best means mathematically. So that's the job of what we call the loss function. If you studied optimization before, this might seem very obvious. This is just what we call objective function and optimization, but we call it the loss function in machine learning. Okay, so anyways, we're going to pick the most natural one, which is least squares, meaning we minimize the sum of squared prediction errors. So the residual sum of squares here, or RSS, is just the sum across all observations of the actual value in your training data set minus the predicted value. This is f of x equals xi. Oops. Your predicted value here, and then you square it at the end. So here's the sort of where the optimization background immediately becomes useful. So the residual sum of squares of beta is quadratic function of the parameters beta. And we already know from the Boyd book what this buys us. A quadratic function must be convex. So a minimum is guaranteed to exist. But this is the most important caveat. It might not be unique. So we'll come back to exactly why this is true. Okay, so using matrix notation, we can write it as this, since the norm of a vector, the second norm is equal to x transpose x, right? And if you plot it, so the residual sum of squares in the beta space, it will look sort of this like this curved bowl like this, and you want to find the minimum. Find the RSS that minimizes the RSS function. Now we know that RSS is positive semi-definite because if you expand the quadratic form, you'll find that the Hessian of RSS is as follows. So this is the Hessian here, and we know that anything transposed by itself is always positive semi-definite. So this is exactly the cone we spent so much time working on in week 3. So we know that positive semi-definite guarantees convexity, which guarantees a minimum exists. But of course, positive semi-definite alone doesn't guarantee the minimum is unique. For that, we need this value to be strictly positive or definite. So when does this inequality hold true? Well, it holds true strictly when the matrix X has full column rank, meaning if your features are collinear, you sit in a sort of flat valley of the bowl instead of a single point, and the least squares stop giving you one answer. Alrighty, so for now, let's just assume we're in the well-behaved case, and so let's actually find the minimum. So we can differentiate residual sum squares with respect to beta and set it equal to 0, which gives us the so-called normal equations. All right, so I just differentiated here and set that equal to 0, and then we've solved for beta. So this beta here, this beta hat, is our least squares estimator, and we have, as you can see, a closed form solution for it for our training sets. So look at this inverse here. So X transpose X. So that inverse existing is exactly the full column rank condition we talked about earlier. So if this was not full column rank, you wouldn't be able to find inverse. So I just want to emphasize sort of the why we did all this optimization before. This very simple idea that a lot of people already know about. It has a lot more to it. It has convexity, positive semi-definite, and rank condition all baked into it. Great. So let's talk about nearest neighbor methods now. So first of all, in least squares, the one we just did, least squares fits a global rule, meaning every single data point. Remember the equation? It used every single data point to fit a global line or hyperplane on the training set. So you can think of it literally as you're compressing the information of your training set down into a handful of weights, or your beta. So the weights contain the information of your data set. So you can literally think of it as information in our data matrix being encoded or compressed into the beta weights. So the second method that we're going to talk about, KNN, or K nearest neighbors, completely throws it out the window. So K nearest neighbors makes no global assumption at all. It simply predicts the price of a new house, xi, by just looking around to the most similar houses already in the training data and averages their prices. So it only looks locally to make a prediction. So that's what this equation is trying to get at, which is that if you have some prediction, xi here, what you do is you just take the other observations in sort of a neighborhood. That's what this n stands for. Take it in some local neighborhood, take all their values, and then average it. So divide by the number or the size of your neighborhood, and just assign that to your new predicted value. So hopefully that makes sense, but if it doesn't, let's look at when k equals 3. So let's say, these dots here are a training set, and we want to predict, the house price of a new house in this location. All we do is find the houses that are surrounding this house and take a look at their values, average them, and then assign that value to the new house here. So, let's look at the philosophies directly. So linear regression compresses. It commits to a global straight line rule and throws away the raw data once it has the betas. k nearest neighbors memorizes. It doesn't compress. It keeps the entire data set around and only does work at prediction time by looking locally. That local only behavior has a direct consequence for training error. So training error is roughly an increasing function of k and is exactly 0 when k equals 1. So let's see why. So pretend instead of k equals 3 in this picture, k is 1. So this is your training error. So let's say you have a point here. So let's say you have a point here and you want to predict what this value is. Well, you look at the nearest neighbor, and the nearest neighbor is, well, itself, which is, it has some value, some y value. Then you take the average of one point, which is just itself, and then you assign it to that point, which is exactly the same value as the point that you use to predict that exact same point. So, you're not really doing anything here. So when k equals 1, your training error necessarily drops to 0. So here's a typical graph of what that might look like. So when k is 1, you have no error. So remember, the training error is defined by residual sum of squares. How close is your prediction to the actual value squared, and sum all of them up for the observations. In this case, all your observations are your training observations, hence why it's called training error. So here's another point. K and n has no weights, right? There's no weights in this equation. We don't learn any weights. So the question is, how do we measure its complexity? For linear regression, that was pretty easy because we could just count how many weights we had in our model. But because we don't have any weights in the K and n, we can't really do that. So how do we even measure complexity of this model here? So ESL says the best way of doing that is to calculate what's called the effective number of parameters. All right, so the effective number of parameters here is for k and n is n over k, where n is sort of the number of data points you use, so it's the number of dots in your sort of feature space, divided by the k, which is the size of your neighborhood. So here's sort of some reasoning behind why this is true. Let's say that n equals 100 and k equals 10. So assume, just for argument, that you have non-overlapping neighborhoods, meaning knowing which neighborhood a house falls into is enough to know its predicted price exactly. So that's sort of a perfect model on the data. Of course, this is just a model for determining our effective number of parameters, but it's a useful way of thinking about it. So you can think of those neighborhoods kind of like a zip code, right? If I know a house's zip code, I can predict its price by averaging every house in that zip code. And the number of zip codes is what the model effectively has to memorize. So that's the count of number of effective parameters. In this case, that's 10. Now notice what happens when k, the size of the neighborhood, is n. Well, then to predict the value of a new observation, what we do is our neighborhood is global. It's not a local neighborhood anymore. You're averaging all the data points. What that means is that you just average every single data point, regardless of whatever new value you're predicting. And again, if k equals 1, then you sort of go in the opposite extreme. The neighborhood shrinks to a single closest point, and you predict whatever that closest point is. So now we sort of have two philosophies sitting side by side, and ESL closes this section by comparing them directly along two axes, bias and variance. How can we think about it? Well, we think in the real world, our data, our X data matrix, is distributed along some distribution. We don't know what that distribution is. If we knew that distribution, then we would just calculate probabilities and do the best we can. But we don't know it. We have to estimate it. Now, if we resample X a lot of times, then we might get different data points. And so, what we're really trying to do, which we'll talk about later, is we're trying to generalize to new data that comes from this distribution. And when a model is able to stay sort of sturdy across resampling of different data across this distribution, then we say it has low variance. The model has low variance because it doesn't vary along with the new data. So linear regression has low bias because it's a very simple model. And maybe here's your data for one sampling, but if I sample again the blue here, it's completely different data, but I get a very similar line. On the other hand, KNN, in this case, let's say K is small. If I sample again with different data, then the line will look a lot different. So we say that the variance of KNN is high. Okay, so what about bias? Bias represents how the model correctly models the true distribution. Now, in reality, it's often the case that the true distribution is not linear. So when we assume linear, we think it's biased, usually speaking, because the true distribution is not biased. So this way, we sort of give up some variance, but instead we take on some bias. On the other extreme, we have KNN, which has low bias because it sort of fits to the distribution, whatever it's given, but it has high variance, as we just said. So that sort of sets up the question that we're going to drive at the rest of the book. Every single model, just some way at trying to lower both the variance and the bias. So the holy grail is a model with both low bias and low variance. And most of what comes next in ESL is really about how do we get closer to that. So that was a pretty eventful first week in the new book. So we first understood the notation the authors will be using. We built the least squares estimator from scratch, and we saw the very same convexity and quasi-semi-definite machinery from the Boyd book. That's already doing the work under the hood. The Hessian with residual sum of squares is a quasi-semi-definite matrix. Whether or not you think about it that way, that's what's really going on. Then we went in the complete opposite direction with KNN, or K nearest neighbors, and set up the bias variance framing that we're going to see constantly, from here on out. Okay, so next week is section 2.4, which is about statistical decision theory, which goes back and asks why squared error is even the right loss function to minimize in the first place. So given how much we learned about in RSS this week, without questioning where it comes from, that feels like the right next stop.